Hello. It's not the afternoon. Hello. I don't care if you're on your school account or not. Salutations. Hola. Do I remember what? I don't understand. All right. I think we've got enough people that I'm going to start. So, hello, everyone. First thing I wanted to say is that I am working on uh, putting your first grades um, into Q. So you already know what your grade is. Every assignment is worth the same amount, and you know how many points you got for each assignment, so you know your percentage. So should be pretty simple. Um, okay. So that should be in by the end of the week. So if you can still submit for all the assignments, but I will have them in by the end of the week. And when I put them in, I'm not going to change the assignment values after that. Okay. Um, Wednesday bonuses are not for extra credit. It's just for fun. Okay. Okay. So today's lesson is going to be fairly simple, fairly short. We're moving on from kinematics. Kinematics is about describing motion. Okay, we learned how to describe motion. Now we're going to learn what causes motion. Okay, and so the thing that causes motion is called a force. Um, so force is a push or a pull with a certain strength in a certain direction. Okay. Um, so a certain strength, that is the magnitude of the force. And then it has a certain direction. So forces are vectors. Um, just like there's a position vector, velocity vector, acceleration vector, there's also a force vector, denoted by F. Okay, so there's a force vector. The units of force are newtons, called newtons N. Okay. And there's a concept called, if you have more than one force acting on the object, there's a concept called net force, which is just the vector sum of the individual forces that are acting on the object. Okay? So however many there are. If you want to add the vectors, so if you have two forces, say F1 and F2, and you want to combine them, you would combine them just like we combined vectors on the very first lesson, which was using the parallelogram rule. So we make a parallelogram out of the two vectors, and then we draw the vector that crosses the parallelogram, and that is the sum F1 plus F2. Okay? So there you have it. I want to talk, so let's do an example where we sort of mathematically compute the net force. Okay? So let's suppose an object is subjected to two forces. Okay? So I'll just put them as bullet points. A 30 Newton force acting in a direction, let's say 25 degrees west of south, and I'll explain what that means in a second if you don't remember. And then maybe a 60 Newton force acting, let's say, 40 degrees north of west. Okay? So let's draw what this kind of looks like. So let's say here's the object right here. A 30 Newton force acting 25 degrees west of south. So let's draw our cardinal directions: north, south, west, east. Okay. So a 30 Newton force acting 25 degrees west of south. So we start with the southward direction, and we go 25 degrees west of that. So east is over here, so we're going to rotate 25 degrees in the westward direction. So maybe something that looks approximately like that. Okay, so this angle right here is 25 degrees, and this length is 30 newtons. Okay, I know that's kind of hard to see, but I'm going to draw it bigger in just a second. Then there is a 60 Newton force acting 40 degrees north of west. So that means we start out with the westward direction, and we go 40 degrees north of it. So maybe 45 degrees is here. So we go a little bit less than that. So something like this kind of. And I'm going to draw this as being twice as long as the other vector because its magnitude is twice as great. Okay? So this angle right here is 40 degrees north of west. If it was 40 degrees south of west, you would have rotated down and it would be pointing in this direction. So that is 60 newtons. Now, if we wanted to use pictures to draw this, okay, or to find the net force, what we would do is we would create a parallelogram like so, and the net force is going to be like that. All right, so that would be the answer to this problem, finding the net force in pictures. Okay, but what if we want to do this algebraically? All right, so what we have to do is write each force in IJ form. Okay, so let's start with the 30 Newton force. It's 30 newtons, and it is 25 degrees west of south. So here's south, here's west, and we are 25 degrees west of south. So that angle is 25 degrees. So how do we get the I and j components of this vector? Well, the I and j components would just be the legs of these triangles, okay? So I can see that this leg of the triangle is adjacent to the angle. So this is going to be 30 cosine of 25. Why is it cosine? It's because cosine is the trig function with adjacent. Cosine is adjacent over hypotenuse. This is the opposite leg of the triangle. So that would be sine. That's going to be 30 sine of 25 degrees. Okay. You want to make sure that your calculator's in degree mode if I give you the angle in degrees. 30 times cosine of 25 is, I'm going to round just because I'm not interested in a lot of accuracy for this. So that's 27 newtons. And then this is 30 sine of 25, which is about 13. Okay. So now if I was going to write, let's just call this one F1. So then that means that F1, and we got to be careful here when we write it in IJ form. This distance is 27 newtons, but it's going downward. So that's negative 27. This is going to the left, not to the right. So that's negative 13 I. So this vector is negative 13 I hat minus 27 j hat. And this is measured in newtons. Okay? Let's do the same thing for the second vector. The second vector has a length of 60 newtons. And this angle right here is 40 degrees. So I can see this vertical component of the vector is opposite the angle. So that's going to be sine, 60 sine of 40 degrees. This is adjacent to the angle, so that's going to be 60 cosine of 40 degrees. So I will type these into the calculator really quickly. This is about 39 newtons. And then this is about 46 newtons. Okay? So if I want to write F2 in vector form, I can see that it goes up 39 newtons. So that's going to be plus 39j. And it goes to the left 46 newtons. So that's going to be minus 46 I hat, measured in newtons. Okay. So now what I can do is I can go ahead and add these together, assuming that these are the only two forces. If I want to get the net force, I would add these two together. So adding the I components would give me minus 59 I hat. And adding the J components is going to give me 12J. And that's measured in newtons. So we can see that this vector goes to the left 59 and it goes up 12. So this is kind of approximately correct then, right? Because see how it goes over much more than it goes up. All right? So that's consistent. Good. What if I wanted to know what is the magnitude of the net force? Okay. A problem that I've seen a lot of you having is that you are adding the magnitudes. So a lot of you would have said that the magnitude of the net force is equal to the magnitude of force 1 plus the magnitude of force 2. So you would have said something like, oh, it would be 30 plus 60 equals 90 newtons. This is 100% incorrect. Don't do that. Okay? You need to find the net force vector first and then get the magnitude of that. So I've answered that problem probably 4 or 5 times since the class has started, where people were having the issue of calculating the magnitude and then adding or subtracting instead of subtracting them or adding them as vectors and then getting the magnitude. So the magnitude is kind of the thing you do in the last step. So if I wanted to know what was the magnitude of the net force in this case, I find the sum of the two forces first, and then I get the magnitude of that. So it's going to be square root of 59 squared plus 12 squared. Which is about 60 newtons. Okay? So that is how you deal with forces. How you manipulate forces. So what are forces used for? Well, they're part of Newton's laws of motion. So the remainder of this lesson is going to talk about Newton's laws of motion. Okay. So the first law of motion you've heard before. This lesson is mostly a review, so or at least I hope it's a review. I'm going over this because I know we have people in the class who have not taken AP Physics 1, or IB Physics, so it's kind of important to go over this. The first law of motion says that objects in motion stay in motion. Objects at rest stay at rest. When the net force is equal to 0. So if any time that the net force is 0, if it's in motion, it's going to stay in motion. If it's at rest, it's going to stay at rest. So if I wanted to say this in as concisely as possible, I would say that net force equals 0 implies that the velocity is constant. Okay, that's the most concise way of stating Newton's first law of motion. All right. Now, I always like to think about when I think about why is Newton's first law true. There is no proof of Newton's first law. All right. It's just an observation about the universe, and but when I think about the alternative, that would mean that objects in motion do not stay in motion, or objects at rest do not stay at rest. Okay, so that kind of means that things are just moving around randomly. If something is at rest, it just kind of could randomly go when nothing causes it to do that. Okay, so kind of the alternative to Newton's first law of motion is just kind of chaotic motion with no rhyme or reason behind it. Okay. The second law of motion is best expressed as an equation. Okay. Net force equals mass times the acceleration. All right. So m is the mass of the object. And just to remind you, mass is a measure of the amount of stuff. Okay, our unit of mass is going to be the kilogram, not the pound, not the gram. We're just measuring mass in kilograms. This right here is the acceleration vector. Okay, and notice how mass is not a vector. Mass is a scalar. So to remind you, a scalar is something that is pure number. It has no direction. It's only magnitude. So here we have a scalar times a vector. So this is an example of scalar multiplication. All right. I encourage you to think about Newton's second law as saying something about cause and effect. Okay? Again, we can't prove Newton's second law. Actually, we can prove Newton's second law because we can prove it from quantum mechanics, but then we can't prove quantum mechanics. So, yeah. So eventually, if you want to prove everything, eventually you get to a point where you just have like a fundamental law of nature that can't be proven. But this is basically saying that in order to cause the motion to change, you need to have a net force to do that. So the motion is not going to just change spontaneously. There has to be a cause to make the state of motion change. So if the velocity is going to change, there has to be a reason for it. Okay. So I always think about Newton's second law as basically stating cause and effect. Then there's a third law of motion, which is the one that says for every action, there is an equal and opposite reaction. So the law of action-reaction. So basically, if F is the force that object A exerts on object B, and F sub B on A is the force that object B exerts on object A, these are related to each other by a minus sign. Okay? So if I punch you with 100 newtons of force, then your body is going to exert 100 Newton force on my fist, but in the opposite direction. Okay, that's what Newton's third law of motion is saying. I give this example every year, so you might remember it, you might not. But if Newton's third law was not true, you would have some crazy things. You would have some crazy things that could happen. So, for example, what if I punched myself in the forehead? Okay, so if I punch myself in the forehead, so here's my fist. Here's my face that I've punched. I punch myself in the forehead like this. And let's say that I exert a 100 Newton force on my face. What if the action was not equal to the reaction, or the reaction was not equal and opposite to the action? Then I could have a force on my fist that my face exerts on my fist that is different from 100 newtons. So maybe this force is only 20 newtons. So this would be a case where action and reaction are not equal and opposite. In which case, what would be the net force? In this case, it would be 80 newtons. So by punching yourself, you have exerted a net force on yourself. And then, when we plug that into Newton's second law, you would then accelerate. So that would mean that by punching yourself in the face, you could accelerate up into the air. If you wanted to fly, you could fly by continually punching yourself in the face. So that is something that is not observed. We can't fly by punching ourselves in the face. So So basically what Newton's third law is saying is the only way to exert a force on yourself Thor's hammer is also a great example of this, because Thor takes his hammer and he exerts a force forward on the hammer. The hammer should exert a force back on Thor, which would make Thor fly in the opposite direction, but instead what Thor does is he accelerates with the hammer, so it doesn't make any sense. Thor's hammer does not work. So the only way to exert a force on yourself is to push off of something else. Okay? For example, if you want to walk, you have to push off the ground. Okay? If you want to jump, you have to push off the ground. If you're in outer space and you want to change your direction of motion, you have to basically push off of your fuel. So if you run out of fuel, oftentimes fuel is called reaction mass, okay? Fuel is reaction mass that you push off of to change your direction in outer space. And what you do if you're in outer space is you bring all that reaction mass with you and you push off of it. You lose the reaction mass because you pushed away from it. And then once you run out of reaction mass, you can't exert a force on yourself anymore, so you are going to just have a constant velocity thereafter. Okay? So, that's the lesson. It's pretty simple for today. I've got some problems on today's quiz that I think are a little bit more challenging, just sort of applications of this. And next time we'll talk about the different types of forces that we can encounter and talk a little bit about something called equilibrium. All right, so that's my lesson for today. Bye, everyone.